Hi guys, our compiler has to generate assembly code, and in the beginning it will be assembly code for the Ulm architecture, of course, but later we also want to support other architectures like Intel and ARM. So what we need is kind of an abstraction layer for architectures or some interface for architectures, which should be general enough so that we at least can support these three architectures, of course, but it will be not too general. We, for example, will not hide the fact that these architectures have registers and only certain type of instructions. But what we hide are, for example, the details about these things. How many registers are available and what is exactly the notation for these different assembly instructions that are available. You will see that most of it is not exactly rocket science. It's mostly about printing assembly code in a nice way. So you will find on the website a complete documentation of the interface and some instructions how to implement this interface. In this video, I just want to show you some of this design considerations for this interface and how to implement some of these functions. In the interface, there will be one type def for identifying registers. In the case of the Ulm, this is simply an unsigned integer with 8 bits, and two functions for managing registers. You can acquire a free unused register with getRegister, and you can release it with ungetRegister. We will make sure in implementation that if you acquire a register, it will always be a register with an ID of 4 or more, so that we can use the typical calling conventions for our functions where we have these reserved registers with an ID smaller than 4. In the implementation, you have to be careful. We will use an array with 256 pools. So that means when we acquire a register, we simply have to loop over these registers to find the next free register. If you would use here simply a for loop like that, then you would have a condition which is always true. So this loop never would terminate. So here we have to use our usual tricks to circumvent that. The release function, of course, simply marks this register as unused. It simply overrides the entry with false. Then, of course, we also should make sure that you never can release a register that wasn't acquired before. So there should be at least an assertion. And we also should make sure that when the program terminates, all registers were released. Some error handling for checking whether we have some internal errors. And then, of course, we also need to generate instructions for doing computations. For example, adding registers, subtracting registers, multiplying registers, and so on. And for this type of instructions, we actually provide two functions. One function where all the operands are registers, where you can, for example, generate an assembly instruction like here. And another variant where the first operand is an immediate value. And then, of course, we also need other functions for generating instructions so that we can load a literal into a register for fetching data, storing data, and so on. In the demo, I will show you how I start with a simple test program that just uses a few of these functions that will be provided in this interface. Then I, of course, also show you how to implement these functions in the implementation of this abstraction layer for the Ulm. And then I will extend this test program so that in the end we have something that produces assembly code that actually can be translated into an executable. And with that, we have a good starting point for going on with our compiler. Okay, let's begin with the test program. I will need to include finalize and of course the header for this interface. Finalize will be needed to check whether before the program terminates all registers were released. So let's already start with that so that we do not forget that. And then I want to acquire a few registers and also release them. And then I also want to generate some instructions for adding registers. So these are the statements for releasing the registers again. And then I want to reorder this so that I actually see that we never get back a register that was previously required, but if we release it, it's available again. And then one instruction for adding only registers and another one for adding an immediate value to a register. Okay. And then we can begin with the interface. And of course, here we begin with the include card. Okay, and then we need this type diff for the registers, and for that we need the standard integer types. And then this declarations for acquiring and releasing registers. Okay. And then also the declaration for this 3 address instructions. Okay. Actually, let's do here some Vim magic. I simply want to repeat this a few times, and then I change this here to 1 and 2. Okay, and here I just changed this function name, and the first operand for this instruction is an unsigned integer with 64 bits. And then I also need this enum constants for identifying the instruction. So I will just implement 2 of them. For you, of course, it will be the exercise to do a bit more. And then I also want to group this instructions where all operands are registers, and another group should be for the instructions where the first operand is a immediate value. So here the usual pattern for doing this grouping. Okay, and now I just have to give this the usual values so that we do not have any gaps in this enum constants. So this becomes begin, and that's it. And now we should be able to generate an object file, at least for the test program. Oh, okay. Typo. Okay, now we're good. Okay, next step, the implementation, of course, of these functions. So let me mark this from here to here, and then I can make skeleton functions out of them. And actually for this get register function, I will provide a complete implementation, which is simply giving back the 0 register first. and unget is doing nothing. This here can be removed. And here first skeleton functions only. But that means now we actually can compile the test program into an executable already without warnings, actually, hopefully. Yeah, okay. And now I want to begin with the implementation of this functions for generating some assembly code. And here I first check whether this enum constant is valid. Also the usual pattern, and this of course can be reused for the other function. Just change it here and here. So that means I need to include this header for assert. And then I want to use here, after checking what kind of operations we have, some print functions. But let me first finish this here. So here I simply check whether it's a supported operation, and otherwise I trigger an assertion failure. And then I want to have print functions like this here, which I can use to make it more convenient to generate assembly code. Function for printing an instruction, for printing unsigned values, for printing registers, and actually even one function for just printing a comma and a new line. So that's what I mean with not exactly rocket science. But you will see this makes it more convenient to implement this interface. Okay, now this can be reused for the other function. I'll just change this here to an R. And this is now a register, so I also want to have a print register function. And in this print functions, I can, for example, hide this messy details about how to use this macros for printing this integer types. So this print instruction function simply prints a tab and then the instruction with some space afterwards. Okay, like that. Then for printing this unsigned integer, here I want to print this in hexadecimal, and I have to use this macro for printing an unsigned integer with 64 bits. Then I want to have this function for printing a register. And here first I have to print a percent sign. So this messy things I want to hide in this static functions. And this register, by the way, will be printed in decimal. Okay, and then this two functions for just printing a comma or a new line. Let's move this here up so that you see it. Okay. Then I have to include this int types for this macros. And I have to include standard IO. And now I already can test this. Okay. And of course, we have to actually implement these functions for acquiring and releasing registers. So here I will need the pool type declaration in standard pool, and then this array with for this used registers. And then here we will not use this for loop, otherwise we have the problem with this overflows. I simply avoid this problem by using a while loop like this. And once I found the used register, I mark it as true, but here I have to check whether we actually had this overflow. And in this case, we get back something which is smaller than 4. And in this case, we generate some error message, and we will call finalize exit. Okay. And for releasing a register, we first check whether this register was actually acquired, and afterwards we simply set it to false. So we need here also finalize included, and now we can check. Okay, so it seems to work. We released register 1, and that's why we got it as register 4. Okay, now we actually should also check whether all registers were released. So we will here also loop over all registers, and here we have to avoid the same problem. We also cannot use simply a for loop in the usual way. So we'll do this with a do while loop like that. And if a register is in use, then I will issue a warning. We also could treat it as an error, but that's up to you. Okay, lucky that this is still 80 characters. Okay. And then we have to register this when we acquire the first time some register. So usual pattern for that. Now let's first check whether we already have some register leak. Okay, seems not to be the case. And now let's see whether this test actually works by not releasing all of them. Okay. So this helps us to prevent certain problems later. That usually will come up sooner or later, at least once. Here we also should check whether this immediate value actually can be encoded in such an instruction. And for now we will simply trigger an assertion. Later we will handle this a bit different. Now let's also see whether this triggers an assertion actually. Okay, so this works. Later we will, in this case, simply first load this immediate value into a register, and then this add variant function will fall back to the function where all operands are registers. So this will be the next step to extend the interface, that we also can load a literal into a register. And first, the literal will be an integer literal. So let's go back to the interface. Maybe here I want to declare some functions for loading a literal into a register. Okay, and this can be used for the implementation. So I will keep it simple here. Just use this loading a zero extended word into a quad word instruction. And in the exercise, you can generalize this so that actually also 64-bit literal can be loaded. But for now, this is good enough. Okay. So the next step now will be that we also want to load a label into a register and then fetch from this label some value into a register. And then we also want to store the content of a register at a certain address specified by a label. So let's do all this at once. So that means we have one more function for loading a literal. Let me just copy this. So this is load label, and this is just a const pointer to a character. And then we have this instructions for fetching and storing a quad word. And also the corresponding store instruction. So here we first have a source register and some address where we want to store this source register. And then we again first can check whether this interface is okay. Just link errors, okay. And then basically this will just require a few more print functions. So first skeletons, and then this function for loading a label is basically the same as loading an integer literal. So let's just copy this, and instead of printing an unsigned integer, I want to print a label. And here I have the move queue instruction, and here I want to print memory location, a register within this parenthesis. This will be another print function, and here basically the same, just a different order. And this actually should be address and also the source, and here this should be destination. Okay, and then I need this new print functions. Of course, you could use directly printf, but you will see it's more convenient to have all print functions in one place. For example, if you later want to replace printf with fprintf so that we can write instructions into a file. Okay, and then also this print mem function is basically the same as print register. We just need this parenthesis. So before and after this register. Okay, and this should do the trick already. Okay, so this part is what we need for loading a variable into a register and storing a result in a variable. Now, what should be next? We want to have a assembly program that actually can be later translated into an executable. So we want to have a text segment and a data segment and a PSS segment. And in the data segment, I want to have a labeled quad word with some value different from 0. And in the PSS segment, I want to have this variable b. And this, of course, are just a few more print functions and some convenient way to access it. So now you see the complete essential part of function main. Okay, so in the interface, we have a few more declarations. Let's put them here. So simply copy paste text, data, and PSS. And then this function for generating data. And for now, just generating labeled unsigned integers. Of course, later we also can generate, for example, strings with a label. And then the usual procedure, first checking whether we have typos in the interface. Okay. And then I can use this for the implementation. And again, first stubs, and then I fill in the blanks. So again, not exactly rocket science. So here we just simply print instructions in this functions for setting the active segment. And when we generate data, for now it's always data with 8 bytes, then we also have to align this label. And later, of course, we can generalize this so that we also can generate data with 4 bytes, 2 bytes, 1 byte. And then we need another print function for a label definition. And let's simply reuse this for print label def. And here we simply print a colon after this label definition. Okay, now this already should work now. Let's see. Okay, not completely. It would work, but I want to have a new line after this colon. And actually I want to have this always when I define a label. So let's see again. Okay, much better. Now, the only problem is if I would translate this into an executable, I would have a problem that I do not have the this halt instruction. And what I want to have in general is some header and some footer. That footer, for example, should have this halt instruction. This header, for example, could initialize the stack pointer, so that with this interface we can easily generate some assembly programs that can be translated into executables. And initially this header will be empty. Somehow my MacBook is kind of running hot, and I somehow have the feeling like in the 80s that I'm typing faster than it can process my keyboard input. Okay, so in this header we currently do nothing, and in the footer we will print this halt instruction. And we will want to halt with execute 0. Okay, forgotten new line after the halt here. So that's easy to fix. Just here, print new line. Okay, and this looks good now. And if I just redirect this into a file, I should be able to run this through the assembler. And I will use the assembler from the last session where we extended the instruction set. So, yeah. And now we actually can check in the debugger whether we can execute this or what happens when we execute it. Okay, so let's rearrange here the windows a bit. Of course, now it's also not rocket science what this program is doing. But here, for example, it's now interesting that we actually load a variable and store a value in a variable. And then, of course, exit with exit code 0. As I promised you, what I showed you was not exactly rocket science. Neither will be the exercise where you have to improve this implementation and extend it. But it will be a bit closer maybe to rocket science, maybe on a brain surgery level. For example, you have to improve the implementation for loading a literal into a register, so that we in general also can load 64-bit values into a register. We will not use here literal pools, but of course this concept could be implemented in this interface or hidden in an interface like that. We will simply use these operators for accessing certain words from a literal and then this shift load operations. And then, of course, also it should be possible to write this assembly code into a file. Changes like that.
Oh, Lionel, glad you could make it. Can I get you a drink?
Yeah, something soft. I'm driving. Parking's an absolute nightmare around here, isn't it? Had to reverse into the tiniest of spaces. Still, I managed it. I mean, parking's not exactly brain surgery, is it? And I should know.
Why is that? Are you a doctor?
Careful. Not a doctor. I'm a brain surgeon. Big difference. Big difference. Yeah, I actually know a joke about this. What's the difference between a doctor and a brain surgeon? One's not exactly brain surgery. The other is brain surgery. So, what do you guys do?
I'm an accountant.
Oh, that's good. Yeah, I could do with an accountant. Filling in those tax forms can get really confusing, can't it? Still, it's not exactly brain surgery, is it? I mean, brain surgery, believe me, is very complex. Are you an accountant too?
No, I work for a charity.
Oh, that's a very selfless job, isn't it? I really admire you. I don't think I could ever do what you do. I say that because it's emotionally draining, not because it's hard. I mean, it's not exactly brain surgery, is it? Which, as a brain surgeon, is what I do.
Lionel, here's your drink. Lionel's a brain surgeon, you know.
Yeah, he mentioned it.
Oh, Jeff, they keep you late at the Space Centre.
As always.
And this food round. Have you met Lionel?
No, hello, Lionel.
So, Jeff, how do you earn a crust?
Well, I'm a scientist. I work mainly with rockets. It's pretty tough work. What do you do?
Why, I don't mean to boast, but I'm a brain surgeon.
Brain surgery? Not exactly rocket science, is it?